About a week ago, we learned about a discovery made by Ørsted in 1819. He said, essentially, that electricity generates magnetism. Moving electric charges generate magnetic fields. What we're going to learn about today is the next logical discovery, and that is that electricity can be generated by magnetism. So electricity generates magnetism, Ørsted 1819. Electricity is generated by magnetism, which we call the generator effect, discovered in 1831 independently by two guys, one an American named Joseph Henry and one a British guy named Michael Faraday. Now, with Ørsted's discovery, there were no conditions attached. Whenever we had moving electrons, we would always generate a magnetic field. With Faraday/Henry's discovery, there were conditions associated with it. We didn't always get an electric current from a magnetic field. We had to have, in order for this to take place, two things. We needed to have a conductor, or a wire, and a magnetic field. And in order for this electric current to be generated by this magnetic field, either the conductor must move. So picture this now. You've got a magnetic field, you've got a conductor, you move the wire. That generates an electric current. Or you could move the magnetic field. So keep the wire steady and move the magnets. That would generate an electric current. Now the third one, which we're going to mention, but we don't talk about a whole lot in Physics 30, you could change the strength of the magnetic field as well. So keep the magnetic field stationary, keep the conductor stationary, and just simply change the strength of the magnetic field. It's these two that we're concerned about in Physics 30, though. Conductor, magnetic field, move one of them. Doesn't matter which one. Move one of them, and that's going to generate an electric current. Now, let me show you a picture that helps describe why exactly this takes place. We've got a situation here where we've got two magnets with a magnetic field that exists between the two magnets. Goes from north to south. Remember, outside of the magnets, the magnetic field will always go from north to south. We've got a wire here. Now this wire has electrons in it, but these electrons aren't moving right now. It's just a wire in a magnetic field. What happens right now? Nothing. If there was a current in this wire, then this wire would experience a magnetic force. We learned about that last week. F is equal to ILB, the hand rule for deflection. But there's not. It's just a wire with electrons in it, because everything has electrons, at rest in this magnetic field. Now I'm going to draw some electrons in here. Now, I'm going to move this wire, like I'm physically going to move this wire. Maybe I'm pushing up on it with my hand. Maybe it's steam caused by boiling water that pushes up on this wire. It doesn't matter. This wire moves upward. And along with it, the electrons that are inside this wire move upward. So now we've effectively got electrons that are moving through an external magnetic field. They experience a force. This is not new. We learned about this earlier on in this unit. Electrons that are in a magnetic field experience a force. Let's see what direction the force on these particles is. We're going to say thumb in the direction of the particles, which is upward, because we pushed it upward. Magnetic field goes from north to south, so we'll say thumb upward, fingers in the direction of the magnetic field from north to south. Palm's going to point into the page. That means the magnetic force on these electrons is this way. Because the magnetic force is into the page on these electrons, then the electrons will start moving into the page. What have we just done? We've just generated moving electrons. We've caused these electrons to move into the page through the wire because of a magnetic force. We pushed the wire upward through the magnetic field. Remember, Faraday and Henry said one of two conditions must be met in order to generate an electric current. You got a wire, you got a magnetic field, move one of them. We're moving the wire upwards. That causes a magnetic force into the page, which means the electrons will move into the page. That's an electric current. We've just generated an electric current from a magnetic field. Now, the last thing we're going to do in this unit kind of combines a couple of the things that we've done earlier on. The last thing that we just finished was a discovery made by Faraday and Henry, and that is electromagnetic induction, the generator effect. When you have a wire and a magnetic field, and you move one of them, then you generate an electric current. Okay? When a magnetic field and a conductor move relative to one another, an electric current is produced in the conductor. Faraday, Henry, whoever you want to give credit to, basically, it amounts to this. Magnetic field causes an electric current. Now, we're going to call this magnetic field number 1, because in a second there's going to be another magnetic field, and we want to distinguish between the two. Let's go to a discovery that we learned about earlier on in the unit. That's the one that was made by Ørsted in 1819. He said that when you have an electric current, that generates a magnetic field. So I, current, generates B, magnetic field. But we're going to call this one B2 because remember that we had a magnetic field generated by a current. This magnetic field is different. This is the one that's generated by the current. Magnetic field produces current. Magnetic field is generated by a current. Now let's combine these two. If we look at Faraday, we know that a magnetic field generates an electric current. If we look at Henry, or Ørsted, I should say, then that electric current will generate a magnetic field. Now you get two of them, two magnetic fields. Magnetic field number 1 and magnetic field number 2. This is what's the crux of today's lesson here. Magnetic field number 2 will always act with magnetic field number 1 to oppose the motion. There will always be a force between these magnetic fields that opposes the motion. So I can move a magnet, I can move a wire, doesn't matter which one, that's going to generate a current. That current will generate a magnetic field. The two magnetic fields act to oppose the motion of whatever was moving, the wire or the magnet. It has to be an opposing force. We know that when there's two magnetic fields, there's going to be a force. Why can't it be a force that helps the motion along? Because if it was, and it would violate the law of conservation of energy. Imagine this. I give a magnet a push nearby a wire. There's going to be an electric current generated in the wire. That current generates a magnetic field. The two magnetic fields make the magnet that I initially gave a push to, they make it go faster. Where did that energy came from? I gave it a little bit of energy to get it started, and now it's going way faster. I created energy from nothing. That can't happen. So, we know there's got to be a magnetic force between the two magnetic fields. It has to oppose the motion in order to have not created energy from nothing, in order to have not violated the law of conservation of energy. Let's take a look at a couple of examples here that we can apply this new concept of Lenz's law to. I'm going to draw a magnet here with a north pole and a south pole. And I'm going to draw a coil of wire or a solenoid. Usually I draw this solenoid or coil of wire with a core inside it, but I'm not going to this time. You can see, though, I think that we have part of the wire in the front and then the dotted line for the wire is in the back. I'm going to draw this around to, not a battery this time, but a symbol for a light bulb. Doesn't really matter what I have there as long as it's some sort of load like a light bulb. Now, when I move this magnet relative to this coil of wire, Faraday and Henry said that we're going to generate a current. Ørsted said that current will generate a magnetic field. Lenz said that newest magnetic field that I just generated will act with the original magnetic field to oppose the motion. So in other words, when I push this magnet closer to this coil of wire will develop a polarity that looks like this. Remember, when I push it, it generates a current. The current generates a magnetic field, and that magnetic field, along with the first one, has to oppose the motion. And the only way to oppose the motion of this magnet is to have a polarity of this coil that looks like this, with a south pole nearby the south pole causing repulsion. Now, that causes a magnetic field inside the coil like this. And if I do the coil rule, with my, this time backwards though, thumb in the direction of the magnetic field inside the coil, which is from south to north, fingers in the front will point up. That means the electric current here will point clockwise through this. Now let's try another one. Let's say this time we've got a coil that looks like this, similar to what it was in the last diagram. But this time we're going to put our magnet over here. Polarity is going to look like this, and we're going to move it to the right. As we move a magnet relative to a wire or relative to a conductor, that generates a current. That current generates a magnetic field. Now we get two magnetic fields. The original magnetic field and the magnetic field that was generated by the current. The new magnetic field, B2, is going to look like this, with a north pole and a south pole. Notice in the first diagram, we repelled the magnet in order to oppose the motion. But that's because I was pushing towards the coil of wire. This time I'm pulling the magnet away from the coil of wire, so in order to oppose the motion, I have to pull it back or attract it with a south pole. The magnetic field inside the coil goes from south to north. If we use the coil rule, that means thumb in the direction of the magnetic field inside the coil, fingers are going to point down in the front. It's going to look like this, with the electric current going up in the back and down in the front.